separating. I've got the blue screen from the camera, and then I want to take it down. Okay. So I just take a beaker of water and a card file folder with a hole in it and put this over there. And now that's water and white light. And I'm going to try to make some turbulence in the water because, not turbulence, but a colloidal suspension in the water. And what I use is sodium thiosulfate. Okay, it's a beautiful crystal. Uh-oh. And I don't know how much. That much. Okay.
Same amount of flavor,
Yeah.
right? Not that much.
Yeah. Good
Not too much,
direction.
though.
Not too much. Right, because if you did too much, everything happens too fast.
So what is that?
This is sodium thio sulfate. Chemistry teacher has it.
And what does it do?
So what it does is it dissolves in water. And it's soluble, so it doesn't provide any particles that are suspended. And what I want to do is mimic the atmosphere. Because the atmosphere is made of particles, and the light comes in at the different frequencies, right? Red, green, and blue.
Right.
And it turns out that those particles interact most with the blue frequencies. They're able to, just like a pinball machine, if that ball is the blue light, all those pins scatter that ball in all kinds of directions. So even though the sun is here, I can look over here and see a blue sky because the red, green, and blue light has come in, but the blue light got a little bit trapped. Some of it comes through, but it got trapped so that anywhere I look, I see the color blue. And that's called scattering. So it doesn't take too many particles to scatter the blue. And that's what I'm going to show you here. I'm now going to add dilute hydrochloric acid. I don't know what it is. Half a molar. Maybe one. I don't know. And the reason I do that is because it makes a suspension. Half, it says, half molar. Yeah, 0.5. Yeah, 0.5. And I'm going to add some. I would say that was a tablespoon, and that's a tablespoon. And it just, you could pay more attention to it. It just determines how quick the reaction goes. Would you turn off the room lights? And what you want to do is you want to watch the side of the beaker and the light that comes up through the top of the beaker and goes to the screen. Oh, there's still some crystals. Now, it's already looking blue to me. Right, a little bit on the screen. But more where you're going to see the blue is here. Because as the light comes up, it interacts with the particles and they start to scatter. See, it's starting to look bluish? The blue is scattering out. And what's going to happen is the blue is going to get completely scattered and never make it to the top of the solution. And so you're going to start to see yellow, orange, and red up here. I don't know what happens to the green. It just gets lost in there. So now it's really looking reddish, right? And look at how blue this is. Okay? Now, in a little bit, towards the top, you're going to start to see yellow because the greens are starting to scatter out and some of the reds, and it looks yellow. And now you see more red is making it through. So apparently the green, we just can't detect it, but look at this right here. So the blue is scattered out down here. We've got the longer wavelengths. Oh, there it goes. Now the sunset is red because of the position of the sun in the sky is lower. Its path through the atmosphere is longer. It's not directly overhead. It's lower. It's going through all this atmosphere. There's more atmosphere for the sun to interact with, so it takes finally that amount of particles to get the red to scatter, so the sky is red. And that's why when the fires are burning, you see a nicer red. And it's a different red too, isn't it? You can go, oh, there's a fire there. You can tell that it's a different red with those kind of particles. Now look at the beaker. The beaker is like a cloud, but it's upside down. So this is the top of the cloud, this is a thunderhead, and this is the bottom of the cloud. And the cloud is black on the bottom just because the light has been scattered in all directions, but never made it down through the cloud. And why you fly over the top of a cloud, and it's the most beautiful thing you've ever seen, is because you're on the same side as the light. And red, green, and blue are all being scattered and reflected back up, and you see this billowy, beautiful cloud. So the sky is blue because it's scattering. Why is water blue? Not reflection. Right. It's scattering. And that's why, because if you've traveled, you know that bodies of water are different colors in different parts of the world because of what's in that water. Right? So if you have, the Mediterranean, it's that blue-green because it scatters that blue-green. And so as you go deeper and deeper in the water, whichever one scatters the least is the color that you're going to see the longest before the lights diminish completely.
Would green be copper?
Green be copper?
What would green be? What mineral would that be?
Oh, why? I think it's salt. I think the salt and the mineral content of the water are able to scatter the longer wavelengths.
Lake Superior is very good.
But it's different than the Mediterranean, right?
There's a lake called Trout Lake, though, that has that same color up by Grand Rapids.
Oh.
The azure really...
It does. So what's up there?
I don't know. I can't explain it.
What?
But that's the only lake in the area that does it.
A bigger closet.
And what's it called?
And
Some
I mean, there's
iron.
even...
Is it, does